Hello everyone, myself Dr. Amit Kumar Yadav, Assistant Professor, School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. Today we are going to see some basic concept regarding this natural language processing. First we will see what do we mean by natural language processing. It is an intersection between computer science, artificial intelligence, and linguistics, and it focuses between computers and human natural language. The important aim of NLP is to understand, interpret, and respond to human language. First part here, tokenization. Tokenization is the process of splitting text into individual word, phrase, symbols. Try to understand this with the help of say hello word. It can be tokenized as hello and word. Then second one say part of speech tagging. It is also called as POS tagging. It involves labeling of each word in a sentence to corresponding part of speech such as noun, verb, adjective. For example, the cat sits on the mat. The tag here, the determiner, cat here, noun, sits here, verb, on and in preposition, the again here determiner, mat, noun. Name entity recognition, it is called as NER. It classifies and identifies name entities in text into predefined categories. When we say categories here, it will be person names, organization, location, date, and more. For example, Barack Obama was born in Hawaii. Barack Obama is the name of a person, Hawaii is the location. Lemmatization and stemming. These are used to reduce word to base or root form. Stemming, it reduces word to root form by removing the suffix. Take example here, running become run. Lemmatization reduces to their base form corresponding the text. Running become run, better become good. Stop word are common words that are often filtered out in NLP tasks as they carry less meaning. For example, the is in. Removing stop word can improve efficiency of text processing. So that's why this stop word is important. If we remove the stop word, it improves efficiency of text processing. Bag of word. It is called as BOW. It represents text which highlights occurrence of word within a document. Basically, it involves creating a vocabulary of all words in a document and then representing each document by a vector of word count. This model disregards grammar and word order but keep multiplicity. Term frequency inverse document frequency. It is used for collection of document corpus. It combines term frequency, inverse document frequency. When we see here term frequency, it means how word appear in a document. Inverse document frequency, how common or rare a word is across all document in the corpus. Word embedding, it is a type of say dense vector representation of word which captures semantic meaning. Try to see the example here, word to vector, globe and fast text. These embedding map words to vectors in a high dimensional space where semantically similar words are closer together. N-gram here, continuous sequence of n items, word, characters. Common example are unigram. It is represented by 1 gram. Bigram here 2 gram. Trigram here 3 gram. Try to correlate this 1 gram with example. Here it is represented by the separated again cat the seat. 2 gram means 2 here the cat again cat seat. Trigram means 3 gram the cat sits. Sentiment analysis. So based on emotional tone behind word, sentence or text, this sentiment analysis classify text into neutral, negative and positive. Syntax and parsing. When we see here parsing, it analyzes grammatical structure of a sentence to identify relationship between words. Syntax parsing, first one can be say dependency parsing, identifies dependencies between word. Example, subject verb relationship. Constituency parsing, it breaks sentence into subphrases or constituents. Example, noun phrase, verb phrase. Machine translation, automatic translation of text from one language to another language. For machine translation, basically uh, we are using say statistical machine learning concept and neural machine translation model. Language model, it is used to predict probability of sequence of word. It is used for tasks like text generation and are often built using neural network. The language model include LSTM based model. Then we are having say text classification. It is used for assigning predefined category to the text. Its example include spam detection, say topic classification and sentiment analysis. Speech recognition, it involves converting spoken language into text. It combines natural language processing with signal processing and is often used in say hidden Markov model and deep learning techniques. Ambiguity in language. It is a phenomena where word, phrase, or sentence have multiple interpretation. It occurs at a different level such as word level, sentence level, and meaning level. Lexical ambiguity, where word has multiple meaning. If we take example here, I went to the bank. Explanation is word bank refer to financial institution or the side of river. Resolution context is used to determine the correct meaning. For example, additional context like to deposit money clarifies that bank refers to a financial institution. Syn- Syntactic ambiguity, it represents when sentence can be phrased in multiple ways due to its structure. So take example here, I saw the man with the telescope. This sentence can be interpreted as I used telescope to see the man. First interpretation. Second interpretation is I saw a man who had a telescope. Resolution, parsing algorithm, and contextual understanding are used to determine the most likely structure. Semantic ambiguity, here sentence have multiple meanings. Example, he gave her cat food. What this sentence mean? He gave food to her cat. Next meaning here, he gave her some cat food. Resolution, semantic analysis and context are used to infer the intended meaning. Pragmatic ambiguity involves interpretation of language in context considering the speaker intention and situational context. Example, can you pass the salt? Explanation, a question about the listener ability to pass the salt. A polite request for the listener to pass the salt. Resolution, understanding the social and conversational context helps resolve pragmatic ambiguity. So here, if you want to do some question here, more than 100 students attended the seminar, 50 of them from our college. The project will be completed in 10 days. The temperature will rise by 5 to 10 degree. Try to solve this with the help of basic NLP concept what we have discussed. Segmentation, what it means in context with natural language processing. It is a process of dividing text into smaller meaningful units. These units may be sentence, word, phrases, or other subunits. It is crucial for many downstream NLP tasks such as tokenization, part of speech tagging, name entry recognition, and parsing. Sentence segmentation involves splitting a text into individual sentences. Word segmentation involves splitting a sentence into individual words or tokens. Subword segmentation, it involves splitting word into smaller units, such as morphemes or subword. This is useful for handling out of vocabulary word in machine translation or language model. Paragraph segmentation involves splitting a text into paragraph. It is important for document level analysis. Chunking involves segmentation and labeling multi-token sequence such as noun phrase, verb phrase, etc. Steaming. Steaming is text normalization techniques in natural language processing that reduces word to their base or root form. It is common representation of word. Steaming are used to reduce dimension of text data, which is useful in search engine, text mining, and information retrieval system. The common steaming algorithms are: first, Porter steaming. It is known for its simplicity and efficiency. It is most widely used algorithm. Lancaster steamer. It is more aggressive steaming algorithm compared to Porter steamer. Snowball steamer. It is also known as Porter 2 steamer. It is an improved version of Porter steamer and it is available for multiple languages. Tokenization involves splitting text into individual units called tokens. The token may be word, phrase, or other meaningful element. Tokenization performs processing and analysis of text by breaking it down into meaningful, manageable pieces. What are different types of tokenization? Word tokenization, as the name indicates, breaking text into individual word. Sentence tokenization, breaking text into individual sentence. Subword tokenization, breaking word into smaller units such as morpheme and subword. So there are different types of libraries for tokenization. First library here, NLTK, it is called as Natural Language Toolkit. Transformers by Hugging Face, Spacai, Gensim. Word embedding, it is a technique for representing word as dense vector of, say, real number in a continuous vector. Traditional methods such as one-hot encoding, it represent sparse, high-dimensional vectors. Word embedding capture semantic relationship between words in a more compact and meaningful ways. The key points are, say, dimension reduction. It reduces the dimension of word. Semantic meaning here capture semantic meaning and relationship between words. So here, if the word is of say similar meaning, it is represented by say similar type of vectors. If we take example here, king and queen may have vector that are close to each other than king and car. Contextual information. It, in this word embedding, learn from large corpora of text and can reflect syntactic and semantic patterns. Its popular embedding are word-to-vector, globe, fast text are trained using various methods to capture these patterns. Applications. Word embedding are used in say various NLP tasks such as text classification, sentiment analysis, machine translation, and information retrieval. So these are the foundation of many modern NLP techniques and models. Word senses. It it means it refers to different meaning or interpretation. If we observe any sentence or word, a single word can have multiple sentence or multiple senses. So first one here, say in word senses, polysemy. Single word has multiple related meaning. For example, bank can refer to financial institute or the side of river. Homonymy. Word have multiple meaning that are unrelated. Bat can refer to a flying mammal or a piece of sport equipment. So these are considered different senses of word and are usually distinguished by the context. Contextual disambiguation. To understand an intended sense of word in a given context. Disambiguation techniques are used. This process is crucial for tasks such as machine translation, information retrieval, and text understanding. Word sense disambiguation. Here, it is a subtask of NLP. It focuses on determining which sense of word is used in a particular context. Dictionary-based method. Here, Lexia resources like WordNet. It provides detailed sense definition and relation. Supervised learning, training models on labeled data. Unsupervised and semi-supervised learning, it utilizes cluster and co-occurrence pattern to inform word sentence. Lexical resources such as WordNet provide structured information about word sense and their relationship. It includes antonyms, synonyms, hypernyms, and hyponyms. Application are machine translation. It means correct translation of word based on their intended meaning. Information retrieval. Improving search result by understanding the context of search queries. Text summarization, generating accurate summaries that reflect the correct meaning of words. Dependency parsing, key aspect of syntactic analysis in NLP and computational linguistics. It focused on analyzing the grammatical structure of a sentence by identifying the relationship between words. Key concept in dependency parsing, dependency relation. The grammatical structure of a sentence is represented by a set of dependency relations. The head is a word that governs or influences another word, the dependent, establishing a syntactic connection between them. Dependency trees. In this tree, each node represents a word and directed edges represent dependency relation. Head and dependent. Head, governing word in a dependency relation. Dependent, the word that is governed by head. For example, the cat sleep. Sleep is the head of cat, which is dependent. Types of dependency. So it includes subject, say noun and noun phrase that perform acts. Example cat, in the cat sleep. Object, the noun or noun phrase that receive the action. Example say ball, she threw the ball. Modifiers, word that provide additional information about another word. Example say adjective, which is used to describe the noun. So dependency parsing models, several algorithms and models which are used for say dependency parsing include transition based parsing. It constructs the dependency tree by making a sequence of parsing decisions based on transition between different states. Graph-based parsing. It constructs entire dependency graph. Neural network-based model. It leverages deep learning technique for learning complex pattern in dependency structure, improve accuracy and flexibility. Application is crucial for various NLP tasks, include semantic rule labeling, machine translation, information extraction, text summarization, tools and resources, SPACI, and NLP libraries, which is a support for dependency parsing. Stanford Parser, a widely used tool for Stanford NLP group. Then NLTK, Natural Language Toolkits, which include different functions of dependency parsing. Word window classification. It is a technique in natural language processing to classify word based on the context provided by surrounding word, which is known as window. It is useful in tasks like named entity recognition, part of speech tagging. How word window classification work? Word window. It is a fixed size context around a target word. If the window size is 3, the window will include the target word. One word to his left, one word to the right. Feature extraction. The features for target word are extracted from this window, and this include word themselves, their embedding, part of speech tags, or any other relevant linguistic features. Model training. Examples say logistic regression, support vector machine, or a neural network which is trained on the features to classify the target word. Sliding window slide over the text, classify each word based on its surrounding context. Suppose here example, consider the sentence, the quick brown fox jump over the lazy dog. If target word is fox and the window size is 3, the window look like this. Previous word brown, target word fox, next word jump. Features for box include embedding of brown, fox, and jump. Example, part of speech tagging. Example sentence. The cat sat on the mat. Assign each word in a sentence is correct part of speech tag. Word window. We will use a word window size 3. One word to the left, the target word, and one word to the right. For the sentence, the cat sat on the mat. Target word cat, window word window, the cat sat. In part of speech tagging, we are using say determiner, noun, verb. Classification, we are using noun. Target word sat. Word window say cat sat on. Part of speech tagging, noun, verb, teaching. Classification, verb. Then target word on. Then again here verb in determiner. Classification here say in preposition. So in this way, this natural language processing algorithm works. What are say different application of this one? Say named entity recognition, classify word into categories like person, location, organization. Part of speech tagging, assign part of speech to each word in a sentence. Chunking, divide a text into syntactically correlated parts like noun or verb phrases. What are the benefit of this one? Context aware, simplicity. Then neural networks for text. The neural networks are like smart algorithms that learn patterns from data. So basic concept here say neurons, nodes. Each neuron takes some input like a word or a number. Then here in neural networks we are having 3 layers. Input layer, text data first enter the network. If we are working with text data, each word or character can be turned into number. So here, Miss Neural Network cannot understand the text directly. Therefore, it should be converted into some number. How it is possible? With the help of embedding or one-hot encoding. After this, it is fed through the input layer. The hidden layers between inputs and output. They do the heavy lifting by learning complex patterns in the data. Output layers, it gives the final prediction like identifying whether a text is positive or negative in Sentiment analysis. Learning. The network learns by adjusting the importance weight of connection between neurons. It tries to minimize error using a method called backpropagation. Activation function. It act like filters. We decide whether a neuron should send a signal forward or not. Text as input. The text is converted into number, that is called as embedding. So this can be understood by the network. Pattern recognition. The neural network learn pattern like word usually appear together, sentence structure, or even the sentiment behind phrases. Prediction. It can predict things like the sentiment of a sentence. Embedding. Represent word or phrases as numerical vector. Why use embedding? Computer can understand number. Therefore, the text data should be converted into number as computer work with number. Therefore, this embedding play an important role in natural language processing. Capture meaning. It means assigning a unique number to each word. Don't capture the meaning of relationship between the word. How embedding work? Word as vector. In an embedding, each word is represented a vector, a list of numbers. The word cat might be represented as 0.2, 0.1 minus 0.1 in a high dimensional space. Similar word, similar vectors. Similar in meaning or context have similar vectors. For example, king might be 0.6, 0.1, 0.7. Queen might be 0.5, 0.2, 0.7. The vectors for queen and queen should be close to each other in the vector space. Training embedding. Embedding can be learned using large text data. Word to vector. It adjusts the word vector so that similar words have similar vector. Globe. Word co-occurrence across the whole text corpus. Learning vectors that capture global statistical information. Bird. Bird create embedding that understand context better. So the same word can have different vectors depending on how it's used. Example, suppose here we are having sentence. The cat sit on the mat. After embedding, the word cat might be turned into vectors like say 0.2, 0.8, minus of 0.1. Mat might be say 0.5, 0.6, 0.1. Its application here say text classification, search engine, machine translation. N-gram models. It is a type of statistical model used in natural language processing. It is used to predict probability of sequence of word in a sentence. It is called N-gram model as it considers sequence of n word at a time. Key concept here, n-gram, for example, unigram 1 gram, single word example the, bigram 2 gram, a sequence of two words, example the cat, trigram 3 gram, a sequence of three words, example the cat sits, and so on. Language model, it assigns probabilities to sequence of words. For an n-gram model, the probability of word depends on the previous n minus 1. For example, in trigram model, probability of word depends on the two word preceding word. How it works? The model is trained on large corpus of text. It uses this count to estimate the probability of word following a given sequence of n minus 1 words. So basically, this equation, this formula is used for a bigram model. So if you consider here a bigram model that trained on say sentence, the cat sit on the mat. It learns probability of cat given the probability of on given sit. If you start with what the model can predict cat as likely the next word. Applications are text prediction, speech recognition, spelling correction, but it has certain limitations, such as a limited context, data sparsity, overfitting. Now we will see what do we mean by perplexity. It is used to evaluate the quality of a language model. It means how well a probability model predicts a sample of text. Low perplexity indicates better model, as it suggests model is better at predicting the text. What is perplexity? Understanding the perplexity. If a model is well trained and predict the text well, it will have low perplexity, means low surprise. If a model is poorly trained, it will have high perplexity, means high surprise. Mathematical. The perplexity is represented by this equation. This part here, the to a sequence of word W1, W2 up to Wn. Alternatively, of this one, the perplexity is given by this equation also. So what conclusion we can make by seeing this one? Perfect prediction. If the model predict each word in a sequence perfectly with probability 1, the perplexity will be 1, meaning no uncertainty. Random prediction. If the model predict completely at random, the perplexity will have will be higher, indicating greater uncertainty. Average case. In practice, perplexity is usually between these extremes, reflecting how well the model predicts the actual text. Perplexity and language model. N-gram models. This perplexity is used to evaluate n-gram model. A trigram model, for example, will have lower perplexity than a bigram model if it is better capture the text. Natural language model, lower perplexity than traditional n-gram models, indicating they are better at predicting the sequence of word. How we can interpret perplexity? Lower perplexity score indicate better model. If one model has a perplexity of 50 and other has 100, the first model is considered to be a better at predicting the text. For example, suppose we are having say language model The cat sat on the mat. If the model predicts each word with high probability, the perplexity will be low, suggesting the model understands the text well. If model predict each word with low probability, the perplexity will be high, which suggests the model is less effective. Hidden Markov model. It is governed by Markov process with hidden state. It is used in speech recognition, natural language processing, and bioinformatics. Hidden state, actual state of a system, are not directly observable. Observable state outputs are observations that can be directly seen or measured. Markov properties. It assumes probability of transitioning to the text state depending only on the current state, not on the sequence of previous state. This is known as first order Markov property. Transition probability it defines likelihood of moving from one hidden state to another. Useful represented in a matrix called transition matrix. Emission probability it defines likelihood of observing a particular output given a specific hidden state. It is represented by emission matrix. Initial state probabilities. These are probabilities of system starting in each possible hidden state. So these are certain structure of HMM. So here is state S, where SI represent possible hidden state. Observation O, O1, O2 up to OM. OJ represent possible observable outputs. Transition matrix Aij represent probability of transitioning from state Si to Hj. Emission matrix represent probability of observing output OK given state Esj. Initial state distribution this pi I represent the probability of starting in state Si. Now we try to understand this hidden Markov model with one example. Imagine we have a person who can be happy or sad on any given day. These are hidden states. We can't directly observe their mood, but we can observe their behavior, whether they are singing or not singing. These are observable states. Hidden state S1 represent happy, S2 represents sad. Observation O1 singing, O2 say not singing. Transition probability a probability of moving from one state to another. It is given by this matrix A is equal to 0.7, 0.3, 0.4, 0.6. If a person is happy, there is 70% chance they will remain happy the next day. If a person is happy, there is 30% chance they will remain sad the next day. If a person is sad, there is 40% chance they will become happy the next day. If a person is sad, there is 60% chance they will remain sad the next day. Emission probability is given by this matrix here. Here, if a person is happy, there is 90% chance they will be singing. If a person is happy, there is 10% chance they will not be singing. If a person is sad, there is 30% chance they will be singing. If a person is sad, there is 70% chance they will not be sinking. So what we observe there, so based on the condition, there will be some outcome, which is represented by these two matrices, transition matrix as well as emission probability matrix. Initial state probabilities. So probability of starting in a particular state is given by say this one. So there is 60% chance the person is happy at the start. There is 40% chance the person is sad at the start. Problem: calculate the probability of say observation sequence. Suppose we observe the person for 2 days. They are singing both days. We want to calculate probability of this observation sequence. Singing, singing using the forward algorithm. Now initialization, we start by calculating the probability of being in each state on day 1 observing singing. For happy S1, we calculate say 0.54. For sad S2, we calculate it as a 0.12. So the probability after day 1 is given by alpha 1, here say 0.54, alpha 2 say 0.12. Recursion, we calculate probability of being in each state on day 2 given the observation so far. For happy S1, S1. For sad, it is given by say S2, alpha 2 of S2 is equal to 0.07. Step third, termination. Finally, the probability of observation sequence singing is the sum of probabilities of being in either state on day 2. Probability of singing is given by this part. So here we get here say 0.4536. Now, what do we mean by Viterbi algorithm? It is used to find most likely sequence of hidden state in hidden Markov model. Given a sequence of observed events, the steps are initialization. So here delta I probability of most likely path ending in state Si after observing O1. Pi I here say initial probability of being in state Si, then probability of OI, probability of observing OI, given that the system is in state Si, store the initial probability for all states. Then here recursion for each subsequent observation, say t is equal to 2 to t, where t is the total number of observations. Compute the most likely probability of reaching each stage J, where j range from 1 to n. This delta Tj max of t delta t minus 1 I into alpha ij into bjot, where this delta t minus 1 I probability of most likely path ending in state Si at time t minus 1. Alpha ij transition probability from state Si to state Sj. BJOT probability of observing OT given that the system is in state Sj. So for each state Sj, also store the state Si that maximize the probability which will be used for say backtracking. Termination, step third, termination. At the final observation T, determine the state S bar with higher probability, say max of delta Ti. P star, it represents higher probability of any path that in that time T. S star state corresponding to P dash, which is the final state, is the most likely sequence. Backtracking. To recover the most likely sequence of hidden state, backtrack from initial state S star to initial state using stored back pointer. Start with S star, the state with highest probability at time t. For each previous time step t, follow the back pointer to the state Si that leads to S star at time t plus 1. After this, we will see the recurrent neural network. So it is a class of say artificial neural network which is used for say for time series data. So unlike traditional feed forward neural network, recurrent neural network connection that form directed cycles, allowing them to maintain a form of memory by processing information from previous time step. The key concept in the recurrent neural networks is sequential data. Recurrent neural network handle data where orders matter, such as sentence or time series. Then we are having say hidden state that carries information from one step to the next step. Bit sharing. The same bit are applied to input. Bit sharing. The same bit are applied to input across each time step. Back propagation through time. During training, errors are propagated back through time, allowing recurrent neural network to learn from say sequence of dependencies. Structure of say recurrent neural network. So input layers receive input sequence, hidden layers receive input at each time, output layer generate output based on say current hidden state. Types of recurrent neural network. Vanilla recurrent neural network, the simplest form of RNN with a single hidden layer connecting back to itself. It can suffer from vanishing oblique exploding gradient problem. So long short-term memory, it is a advanced version of RNN architectures. It includes gates, say input, forget, and output. Then we are having gated recurrent unit, a simplified version of LSTM that combine the forget and input gate into a single update gate. This is an architecture of say recurrent neural network architectures. So here we are having say input layer, hidden layer, again here hidden layer, this is called as the output layers. So what are say workflow in say recurrent neural network? So first one here say the input at each time steps processed and the hidden state is updated to reflect past information. Loss calculation, model prediction, and the actual target. Back propagation through BPTT. The gradient are computed and the weights are updated using back propagation over multiple time steps. So one of the major problem here say vanishing gradient and exploding gradient. What it means? Vanishing gradient and exploding gradient are two common problems which is encountered when training deep neural networks. especially recurrent neural networks. So this arises due to in back propagation, where gradient are propagated back through the network to update the bits. Vanishing gradient, it occurs when the gradient become extremely small as they are propagated back through the layer of a neural network. This result in extremely slow learnings. So this is one of the say major problem in say recurrent neural network, because here gradient need to be propagated through many times and information from earlier time steps can get lost. Why does this happen? Because during back propagation, the gradient are multiplied by the bits of the network at each layers. If these bits are small, example, values between 0 and 1, the product of many small numbers lead to even smaller numbers. As a result, gradients shrink exponentially as they are propagated back, leading to vanishing gradient. Slower learning, the early layers of the networks learn very slowly or not at all because their gradient are nearly zero. Loss of long-term dependency in RNN, the network fails to learn the relationship from far away time step. Why it is happen? Because the gradient diminishes as it move backward. What do we mean by say exploding gradient? When gradient grow exponentially during back propagation, it leads to large update of network's base. Due to this, model parameters become unstable and training process too diverse. Why does this happen? If the weight in the network are large, greater than 1, gradient can exponentially grow larger as they are propagated back through the layer. It leads to increasing larger update which can destabilize the model. What is the consequence? The loss function can fluctuate widely. Divergence, the model might fall, fail to learn and diverge, causing error and numerical instability. To remove these issues, we are having say LSTM, that is called as a long short-term memory. It is used to overcome the limitation of traditional recurrent neural network, particularly vanishing gradient problem. LSTM are useful for tasks involving sequence where long-term dependencies are important, from natural language processing and other sequence data tasks. The key features of LSTM, it has memory cells. LSTM has a memory. It can maintain information over long sequence, allowing them to capture long-term dependencies in the data. It has gating mechanism, three gates, forget gates, decide which information to discard from the memory cell, control which new information to store in the memory cell, output gate, it regulates what part of memory is used to compute the output at each time. So this is the figure of say LSTM, which is showing forget gate, input gate, candidate memory and output gate. Now architecture of LSTM, it consists of cell state, which is the memory of LSTM unit, hidden state, output of LSTM unit at each time step, which can be passed to the next unit. Forget get control what portion of the previous memory to retain. Input gate determine how much of the input should be added to the memory. Candidate memory, say temporary memory update based on input. Output gate control how much of memory affect the next hidden state. Final memory update and the cell is updated using both the forget gate and input gates. Why use LSTM? It is used to overcome vanishing gradient problem, as we have seen in traditional RNN struggle with learning long-term dependency because gradient diminishes as they propagate back through LSTM. Capturing long-term dependency, particularly used for tasks where the context over long sequence matters, as in speech recognition, machine translation, and text generation. Flexibility, LSTM can effectively learn when to retain or forget over medium, highly adaptable to various type of sequential data. What are the different application of LSTM in NLP? First one here say language modeling, machine translation. Then we can use it in say text generation, sentiment analysis, speech recognition, named entity recognition,